not scheme of things that we would like to follow. Okay, the first part is you should understand what is happening in the system. Okay, and that too with an additional constraint that you have to understand how things are happening dynamically in the system, unlike any what you call any other process. So it won't be sufficient if you just get a detail regarding how things are happening in a steady state manner. That information may not be. It is not sufficient for you to do any further analysis if you are interested to do a control. So the first part, so that's what, if you recall, that was the need of us being trained in the process dynamics part first. Then we will look at the control, because unless we don't know how the dynamical system operates, okay, we may not be able to say anything regarding how you be able to control, or how do you be able to automate the overall process. Okay. So technically speaking, then what we'll have to do first? We'll have to understand how the dynamics works. Okay. So for which again we'll have to look at the problem from a modeling framework, because how will you predict how your dynamics is going to vary and things like that. So the first part of that is understand how the system works. Okay. Then we will use those information in doing the control. So again, so this part, whatever we are going to teach, maybe in 1 or 2 lectures, is also known to you from some other context, because you are not learning modeling for the first time. You might have learned transport phenomena, you have learned fluid mechanics, heat transfer, so on and so forth. So modeling as a generic exercise, you might be knowing much before. Okay, any questions, any confusions before we start? If there are no more confusions, I will just start with some anecdote. Okay. See, what is a model? So model is the best approximation of a real process. So you cannot play with the real process directly. Why? Because let's say nobody would allow you to go and do some experiments in the real chemical plant where it makes products worth million what you call dollars, and do some experiments and make the entire thing kind of collapse, so that the one aspect is the loss of the product. Okay, so the other aspect is what I would say. One aspect is of course the loss of product. One other aspect is you cannot kind of play with the equipment. There are safety issues related to that. So what you could do, you would have to see their model, assuming that the model is the best approximation of the real process. It is just not an what you call assumption. So rather you will have to choose a model that is a real approximation of the process. So you cannot just say I have taken some random model, okay, which do not have any what you call performance or real behavior compared to the original system, then started working on. You'll have to figure out a model that is a best approximation of the real process. So the problem here is that most of the time models tend to fail, but some aspects of it is useful. Why? Because you cannot integrate each and every information of the real system in a model. You will be able to you try your best to incorporate them maximally, but of course there is a likelihood that you might miss something. And what is the problem? So see, model development of the model is not the key. You see that? So how is this exercise goes? So how this exercise works? So this is the real system, okay? So you would assume that this is a physical plant, and there are innumerable inputs to the system, okay? And there may be multiple subunits, there may be multiple outputs, so there may be multiple subunits inside, okay? In fact, there may be many subunits. So eventually, you would tend to see as an input and an output. So this would be your feed, technically speaking, if you use a chemical process plant or some, then output, of course, is your product. So it is impossible to capture all those dynamics directly in any way. Even if you are a very good mathematical modeler, you may not be able to capture each and every what we call intricacies associated with. So first of all, what we need to understand with respect to model is a mathematical approximation. So you are talking about maths, right? Mathematical models or a simulated model. So there is, even if you see a simulator, behind every simulator, you are basically solving various model equations. So what is the problem? So when we do a mathematical model, so there are two problems here. So not problem, I would say two challenges. One challenge is accurately model. How accurately you can model? Accuracy or answer. Accuracy of modeling. Okay. So this what? So let's say you have a good team and you finally were able to model the system very accurately. The second challenge is you have to solve them. Okay, the solution of so modeling won't give you anything, right? Solution of your model is the problem. So why? So what is the problem? So see, your models are basically you're talking about dynamics, right? So essentially you are not talking about algebraic equations alone. If it is just an algebraic equations alone, then it's a steady state problem and it's much more easier to solve. So when we start looking at a dynamical model, so then it could be ordinary differential equations, fine, partial differential equations, many, so vector, tensor, so on and so forth. So solving, so basically then you have learned about numerical methods course. So see, there are various aspects of it. You have to solve them in, see, your decisions as we are looking for, you have to take a decision in a second. Your decision making in a second. So you need every information regarding how the dynamics works probably within seconds, or let's say a few seconds. So let's say if we in a second, maybe if you find to be too much an overburden concern, it could be uh, some few seconds. So will you be able to solve this ordinary differential equations or partial differential equations in such a short time? Because eventually speaking, they are all computationally complex. Then there are other aspects comes in. Most of the ODEs, ordinary differential equation and partial differential equations, are solved numerically. So there is no explicit solution. I hope you understand what is the difference between explicit solution and numerical solution. So you don't have a single equation that gives your dynamic output with respect to time and input. You have to iteratively find out. So numerical methods, then if numerical methods are not really fast. Numerical methods are not really fast. Why? Because it is a function of step size. Then there is a big problem called convergence and so on. So eventually speaking, model, so when we think that the challenges is not only in developing accurate, what you call, accurate, so not only developing the accurate model, let me correct it, accurate modeling. So let's say even if you succeed in developing a good model, your problem is solve them in a fraction of a second to get all this information. So all of this is a what you call uh, is a matter of huge concern. So this is what we are trying to say. And so so let me also say something. So the most important aspect is the assumption that you brought in. So this assumption should be, see, modeling is a toy game. You can do anything and everything in the computer. So you can have an assumption saying that, so see, eventually, let's say it's all up to you what you do. You can also say that under certain circumstances, when, so like, you can take a very, what you call, unrealistic assumption to make a model. It would give you a model, but are they valid in real life? So that's a big problem. So you can, whatever assumptions that you consider, so on and so forth, for instance, most of the things, reaction, you assume equilibrium conversion and things like that. This may not be the case real. If you don't assume that, the result that you are going to get may be categorically different to whatever you have initially assumed. So this assumption play a key role. And of course, it's an art. You have to have a, see, the problem is what? So there are three conflicting factors. Accuracy. So the more you accurate, the most likely that your model will be very more complex. Okay. And the third aspect is computational. Computational. Computational related problem. So see, it's like this, right? So if you are making a model more accurate, eventually means that you are making the model more complex, and you increase the computational demand. Or because this is what we need to make a decision in maybe in a second or a couple of seconds, because you need to have faster solution. Okay, so let's say go the reverse. You made it computationally very easy. The model complexity will be less. Okay, then you're compromising on the accuracy. So this is a very, what I call it as vicious circle. This will keep on happening. So as an engineer or a domain expert, it's up to you to kind of trade off, okay, between all of this. It's technically a trade off. Okay, so now coming back to, so whatever I am trying to say, this is mostly, so let me also talk about something else. So there are three classes of models. One is called physics-based model. Okay, it is also called first principles based. Okay, second is fully data driven. I'm sorry, let you go. It is fully data driven. So it is, yeah. So this is basically the ML based machine learning or whatever you would like to call. And third is a sweet spot between one and two. It is called basically gray box. So it is like a combination of one and two. So data-driven models are also called black box models because the black box in the sense that you don't worry about physics when you do a data-driven modeling. Your aim is to only make things work. So machine learning or data-driven based model doesn't care about the underlying physics. Why? Because your aim there is to just model the data which is expected to carry the most information of the process. So you are not worried about that your data is behaving or rather following physics and so on and so forth. So so here what you gain here it would have more generalizability because it mostly coming from physics. Okay, but again the difficulty here it is tedious. So whatever I told previously all would kind of affect over there. While here this is faster and maybe I would say more feasible because you only have to look at the data and you use whatever uh, what I would say you will have to only develop a model based on the data. Okay, and okay, the problem here is it may not be generalizable because it doesn't lack physics, but you could do something to make it work. And the third is, as I told, a sweet spot between middle ground between one and two. So some part of the model would be physics, which you cannot inevitably you cannot compromise. Whatever you cannot compromise would come as physics part, and and some part is definitely you are unable to model very due to its complexity. You take its help from data-driven model. So they are called gray box model, which is generally the most widely used modeling strategy in chemical engineering or many other. So now also what is known as, so there is something now coming up which is known explainable AI, which is of course, these are all classical methods, textbook, explainable AI methods. Here also you would see that, so see that the problem that a machine learning based model or a data driven model would have, it's the lack of generalizability. You may not be able to derive any insight out of it. You will be able to use it for your application, it would work. But like let's say if you need to gain some insight regarding how two variables are co-varying and so on and so forth, that information is very difficult to extract. So due to the advent, of course, so people were not looking at data-driven modeling in a great extent previously. Now, because there is a renewed interest and a lot of people are working on this area. So now there is a push to have what is known as explainable AI-based model. You can so forget about the physics for some time. So can I get some of this information? Some can I extract or can I retain some of the information from the data itself that satisfies the physics? Okay. So they are basically called explainable AI or very. So this explainable AI is a more what I would say technical term. People would like to call it as physics guided AI or so on and so forth. So yeah, so we are in this era. So initially, so this was the oldest approach because data-driven approach came in prominence. It's not very. So this is the oldest one. Okay. So then you have, of course, this progression comes in. Then, of course, if you have A and B, there is no. It's not very difficult to combine A and B to make an A plus B. While this the last one is standalone. It's completely new. Okay, so any questions here? Any questions before we move on? Hello, any questions?
No, sir.
If you have any issues, feel free to stop me. Of course, this now contents again, you're not concentrated into a quantitative analysis, more qualitative. But if you find anything not clear, please feel free to stop me. Okay, so if you have a model, there are multiple advantages. So you will be able to use them to understand the process, okay, because you can simulate and see what is happening. Okay, so these two are our interest. Of course, optimize the process design and operating condition is part of advanced process control. So this is basically advanced process control kind of a thing. While designing the control strategy is directly coming under our ambit. It is basically proper process control. Okay, so and the third is training the personnel. So this has nothing to do with any other thing. So let's say if you are joining new in an industry, or you will be able to understand how things work there, right? So you will be able to train them by playing with the models. So basically, they are simulators. You heard about flight simulators, how it works. So the let's say an aircraft you need to fly, or even just start flying, you should be proficient in terms of the flight simulator. So if, if you are good enough in simulators, then you are ready to do hands-on. So the same things work in training the operating personnel. So once you are comfortable with how the simulators work, which is expected to mimic the original process to the best extent, then you will be able to go do what you call you'll be able to do your hands-on. Okay, so many of the things now, whatever we see on the slide, I have already mentioned, right? So the major category of this modeling approach is first, like oldest, I would say, first principle. So there are various names like fundamental, physics-based, chemical. So basically, first principle means that you have used the physical understanding of the process. So most of the like the simplest first principle model that you all know is for material and energy balance. So it satisfies the physics. Okay, so then if you want complex, you want to add finer detail into the system, then you would add heat, mass, and momentum transfer. If needed, again thermodynamics. Okay, so now till now we are only talking about the physical system. Then you would talk. Let's say if there is a reaction happening, you add chemical kinetics, so on and so forth. So the problem is, you see, you look at from where we started. Okay, you initially had material energy balance, then you had the transport details. Okay, then you added the thermodynamics. Okay, then you added the chemical reaction, then property relations. So see, it will become enormously complex when you progressively add them. You see, this is one. Let's say this, if I call this as one. Okay, now this is all of this. I will all like to call it as transport. Okay, then you add thermodynamics. Okay, then you add the reaction engineering to it, and then you add the physical property relationship. So finally, you are so like, as I told you, would really might get a good model. Sometimes you may not be able to. So let's say it's such a complex process, you may not be able to write the material and energy balance due to the feedback loops, n number of feedback loops in the system. So even though it's good in paper, and if you it would be great if one could do it, it is computationally intensive. So as I told, developing the model is one aspect. You also need to solve it if you need to make things work real time. And all of this complexity, model complexity is entirely depend upon what all assumptions you are adding over here. So, so what I told the investment. So this, so again, industry, right? Everything like, unlike any academic exercise, they are only looking at the returns. So let's say you are working, even you, let's say you are an entrepreneur trying to develop, so you own a chemical plant, okay, and you need to model, you need to have a model of the system to do something further. Okay, then you called your what you call chief technology officer or whomsoever you were a technology person and figure out, okay, I need this to be done. Figure out a roadmap. And you also tell I am a Puritan. I can only work with first principle model. Others I don't like. They're all not really nice. So he went and did back of the envelope calculation and came up with, okay, you need a team worth 5 people for 2 years with an investment of, let's say, uh, what you call 1 CR and things like that. Okay, then you will definitely think twice and you will ask for, is there any alternative? Because investment, right? Is it useful forever? So then he will say, okay, so there is another way. I cannot do it by first principle, and people now started using machine learning based modeling. Okay, and that seems to be faster. You don't require 2 years of time to develop such model. Then again, you will ask, what is the back of the envelope calculation? He came up with, okay, this will only cost you 80 lakhs and 1 year time. So as a promoter or as an investor, so technically speaking, you only need things work, right? So why do you need to spend too much? So this is a big problem. So first principle models are mostly expensive and time consuming to obtain. But of course, there are real good advantages. They are good for extrapolation, scale up, and so on and so forth. Because see, physics, it is fully physics based. So, and as I told, physics is fundamental physics. If it is correct forever. There is no confusion, right? If you could capture the physics well, for instance, law of gravitation, there is no. Of course, you would say that there are improvised versions of relativity theory and things like that. Gravitational theory is fundamental. There is no, because it fully obeys the physics, even though how older, though, even though it is a very older thing. So once you develop, it is fundamentally correct and it is going to serve forever. But like, you need to do that is the question. And also require no experimental data or any data because see, you are doing it from the physics, right? So physics technically do not require a laboratory scale experiments. You are deriving the assumption, writing the balance, assuming various things, and so on and so forth. Another aspect, as I told, is the black box or empirical. I also add this machine learning based. They're all the same. And eventually, what you are doing to do, you are trying to fit a model. You basically call fitting a model. Of course. Model structure is predefined, be it a linear regression. Okay. You know what is the structure of the linear regression? You only need to fine tune the parameters, be it a neural network, huh? Everything. The model structure is prefixed. And what you would do is you would fit the data into this prefixed model. So that's why it is quickly because your model structure is fixed, right? Your what you call your effort is only fitting or basically if you want to have a more refined word, training a model. Structure is fine, you only need to train it. As I told, model structure is subjective in the sense since there are, it's like a shelf. Okay, you will have lot of models available. It may be linear regression here, it may be neural network here, it may be support vectors here. It may be decision trees here, so on and so forth. So you as a modeler, you have to go and pick, okay, this is my pick. Okay, so if I picked, and let me do the training. So it is a bit subjective, but that's fine. Like, but it makes things work. Okay, so the major issue in this case is this extrapolation. See, it is all designed or developed from data. So data is the evidence. Let's say if your model to know, let's say basically you have a data and you train train your model with the data. Let's say if you have not seen a data anytime, and your model will also doesn't know that such a data exists, and model will also don't know the behavior of the system when they operate in that condition. So the key aspect in black box or empirical modeling is the, I would say, representative data. Representative in the sense that you have to have that belief that my data history is good enough to support my overall operational range. I don't have anything hidden. I have everything in the data. That's the hypothesis. Unless if you don't have it, like if you have a very narrow operating range and you would like to develop a model, a global model, it's going to be difficult. So other one is gray box or semi-empirical model. So it's a, as I told, it's a sweet spot. It's between. So some part of that would be uh, physics based, and some part of that would be machine learning or like the data driven based, and so on and so forth. And for large scale, so of course, I did not add it here. So because it's, of course, it's not there in the text. That's why I did not add. But of course, the explainable AI kind of models. So any questions here? Am I audible? Is there an issue?
Yes, sir.
Hello. Hello.
You're audible, sir.
Perfect. So yeah, I could hear you. Thanks. Thank you. So okay, so we have a limitation to cover all of this. So then, as I told, then the six will be big course on modeling. So we will start with first principle models that we have learned age old and we know how it works. To start with that, okay, and we might touch upon little bit on data-driven model in a very brief fashion, and we will go ahead. This is our plan. Okay, and how do you what are the steps that we need to look for? So we'll have to of course state the modeling objective, which variable that you need to model, and what is the detail that you need to do. So the level of detail, of course, the accuracy and objective. So this has to be a prior because you can do one thing in many different ways. Okay, a good way, a very nice way to have a schematic. Okay, write down the assumption. Try to have a parsimony, which means trying to have something very simple rather than things complicated, because that could have an impact on the either in the modeling phase or in the solution phase, so on and so forth. So if you check for spatial variation versus temporal variation, so that would give rise to whether you need to have a ODE or PDE. So you need to look for the conservation equation that would bring in sometimes or an equilibrium relationship in thermodynamics that would bring in algebraic equation. So most of the physical system you would deal with will be generally called as DAE type. So DAE means differential algebraic equation. So differential equation, of course, to capture the spatial and temporal variability, and an algebraic equation to capture some of this conservation equation, mass, so on and so forth. So first of all, once you've done this, you have to check whether the degree of freedom analysis, whether you will be able to solve it or what. Okay, then is there any scope of further simplification? Once this is done, so let's say if you are done with that much, you could identify the variables in the model as disturbance variables, manipulated variable. Okay, because I'm not explicitly saying control variable because that is something that you know from the starting, and that is what guided in the overall model development. So any questions as of now? No questions? Okay, so predominantly we would definitely use mass, component balance, and energy balance. We will be able to get at least uh, we may be able to we will be able to use at least one of this for developing the own models. So conservation laws are the key, and you know, like this is something that you have done. So let's take basically a recapping exercise. So consider a still tank heating process. Okay, so you have a stirrer that kind of rotates inside the a heater that makes its temperature uniform. Okay, you have a feed in and feed out. So inlet temperature is marked with the subscript I. Outlet temperature is just left as it. Ti means that they are all at the inlet, and this is the outlet. And you are heating it, like you have a heating coil that supplies the heat. Q, which once the heat is transferred into the fluid here, the stirrer would rotate to make things uh, the heat uniform. So let's say if you would like to develop a model that how the temperature profiles, and let's say before we go ahead, so let's say you wanted to control the temperature. So we have to list out the objectives. You want to control the temperature of this tank. Okay, so then we go back. So if you need to do the control, you need to know how the temperature varies with respect to time. So we should know the model of temperature as a time. You see, that is what we are doing over here, correct? Yeah. So you are trying to model the temperature of the tank, which is T, dynamically, which means that with respect to time. So your objective, the overall control objective now dictated what to do. That's why I told once you have to control the temperature of the tank, that would give you the controlled variable. Then you will be able to develop a modeling objective associated with. Okay, so then you need to know how it is varying with respect to time. And now you will come back and try to model this. Some assumption that you always, so you probably need to assume perfect mixing. Okay, hold up is constant, and assuming the inlet and outlet flow rates are equal, density is and heat capacity is constant. The minimal heat losses. Okay, so there is some work happening. So see, your heat, you are using a stirrer to stirrer is rotating inside. So what is the total energy? So assuming that the changes in the potential and the kinetic energy can be neglected, because the heat energy change, the heat change is much higher than that. And also the net rate of work can be neglected because of the heat transfer and convection. So you have the, so see, the rotation of the stirrer might not be generating enough work that can be converted as a corresponding heat energy into the system. So these are some reasonable assumptions that if you need to remove one, okay, you are free to remove one. If you need to add more, you are free to add one. So basically what I'm trying to say, it's for us to fix this. So let's say so see, you have an objective now, control the outlet, the temperature of the reactor or the tank. Okay, then you came up to the fact that so for which I need to develop a model. Okay, then I went back one step ahead and say that, okay, before developing the model, because we are doing a first principles based model, because there is no sensor. So see, if you need to develop a data-driven model, you need to have a lot of stored data, because data history is something that would help you to develop this model. And you will say that there is no sensor here, so there's nothing recorded. I don't have any data history. So I have only my understanding about the process, how it works. And overall, this process doesn't seem to be very complex. So the investing in first principle modeling is not a bad idea, because you have only one unit and all of these operations are known to us. It's just a heat transfer. So there is no harm in going with this. So this is the argument that should help us to choose the first principle model. So let's say you have 10 such reactors in series. Okay, everything has nice sensors and all the data is stored, and there are multiple reflexes. One tank is connected to two, three, four. Then there is some feedback, recycle. Then you could definitely think of not doing a first principle modeling because of its complexity. And if you say that, okay, I have a lot of sensor giving you good data which is safe, I could also think of looking at it from a modeling from a data-driven perspective. So I hope this aspect of the design stage is clear to all of you. Any questions here? Any questions? Perfect. So if you have any, please feel free to ask. Okay, so basically you need to do a balance, right? So how do you do? Generally, you do an energy balance. Let's say you are trying to do. Eventually, you have to know that you need to control the temperature. So controlling the temperature is definitely, it's not a mass balance problem because you are adding energy. So it's an energy balance problem. So you try to do an enthalpy balance. So change in the internal energy is equal to the rate of what you call heat in and the heat what you call uh, mass flow rate and its enthalpy per unit mass plus heat transfer to the system. So then again, so the point here is a very nice enthalpy balance we have written. So we will now see that there is no temperature variable in here. So eventually you need to control temperature and there is no temperature variable in the model equation 1. So what we should now try to do is use our smartness to bring in this variable inside this equation somehow. You could consider trying to see how enthalpy or heat could be developed to connected to temperature, so on and so forth. Okay, so now what we are trying to say, let's take the left hand side term only. So pure liquid, this is just a water assuming that, and under moderate pressure, it's an open system, there is no further pressure. Okay. Under moderate pressure, the internal energy change is equal to the enthalpy. So U change in internal energy is equal to enthalpy, and H of course would be equal to CD. So what would eventually happen is, and U, what I would say is, you change it. The internal energy you can call it as rho, course mass by volume times uh, So basically you are talking about a specific variable, so multiplied by internal energy per unit mass. If you unit is the internal energy per unit mass, okay, you will multiply. You have to of course multiply by mass, and because the mass is not really available, you know the density of course and the volume of the liquid. So u in by dt, du in by dt would be rho Vc dt by dt. Okay, so now we have broken down the part 1. So now let's look at the part 2 of it. Okay, h hat. Okay, c dt basically. Then delta of wh would be equal to w times h minus h. Okay, and now I'll write t minus. So it is delta, right? So delta would mean that w h hat. Okay, so I will keep this w guy out. Okay, so h hat minus, so it's a change, right? So it changes with respect to some reference variable, and you will have h hat minus hi, and h hat you can call it ti minus t ref, and h you call it t minus t ref. So what you would really see, so now you can appreciate in equation 2 and subsequently in equation in the last bullet, you could bring out the temperature variable in the model, which was not there in equation 1. Okay. Now what you could do, you can all plug in over here. So left hand side would be rho Vc dt by dt. Okay. So here there's a TRF, it cancels out WC into Ti minus T because there is a T here, and of course Q. Then how are you supplying heat? Okay, so it could be, so the Q stands for heating, correct? So you could supply heat by a heating coil, or you could supply the heat via steam. Let's assume that we are supplying heat via steam. Okay, so then Q would be Ws times Hp. Then you would also add that over here. So this is the dynamical model. So you see everything is varying with respect to time. It is dt by dt. Your t is a time varying variable. And what is the steady state counterpart of it? The left hand side would be equal to 0, will be equal to 0. And assuming, let's say, t become a steady state t and flow become a steady state flow. This is what the dynamical steady state equation corresponding to this dynamic equation. So equation 5 is what we generally use because that is what mostly the simplest case, because assuming that there is no variability in the temperature, this is how the energy balance look like. So this is the true energy balance considering the variability. So I will not move further. I'll stop at here, and if you have any issues we can discuss. Otherwise, I will continue this in the next class. Any questions from anyone? Aditya, Aranya, Ashi, Adira, Ayush, Padavat. I am just reading out your name because there is no way that I could see you, and somebody is on hold also. Kartikeya, Kartik, Kamal, Jackson, Ishika, Harshita. Any questions so far? Anything that is unclear? So I am anyway. Pardon me, Dev.
No, sir, I don't have any.
Hello, Dev.
No, sir, I don't have any questions.
Sir. Cool. So anyway upload. Thank you. So I am anyway uploading the notes beforehand. It may be a good idea if you could just at least browse through it. You don't need to kind of read it extensively. Okay, because just to have a quick, what I would say, uh, understanding. So anyway, so most of these things are known to you beforehand because I who have either learned. So I hope you have learned the heat transfer, I suppose. Have you?
Yes, sir.
Anyone? Yes. Of course, the transport you would definitely know. So I am not telling anything about that. And we will only use it as a cursory tool because we are not learning heat transfer or transport. We are only trying to understand how the model development is useful for us. So we will stop once the model is developed, and that's all about it. So if you don't have any more, what I would say, doubts, I think we shall close the session now, and I'll see you tomorrow. And I think Friday is a holiday.
Yes, sir.
Correct.
Friday, yeah,
So
Friday.
I generally do not prefer to take a class on a weekend. So we can leave the as it is, but if you really need to come for a doubt clearing session, I can keep it open, but I do not prefer to take a class on Saturday. It's up to you. Somebody can tell me. Or we can pull up everything. And if you really need to open up a slot, we could do it in next week as well. If somebody would want to say something. So Hemant, I guess.
So Saturday has Friday timetable.
Friday timetable is on Saturday. So generally, I do not prefer to have a class on a weekend. So either I would upload a video if I need to do, but I am not going to take a live class on Saturday.
Yes, sir.
Okay?
A video will be fine.
Okay.
Thank you,
Okay, guys. Then bye bye.
Yes, thank
Bye.
you.
Thank you, sir.